Hey everyone, my name is Daniel Zhao and my Z ID is z5479971. So just to jump right into it, what are the Kepler's law? So the Kepler's first law, what are known as the law of ellipses, states that all planetary orbits around the Sun follows an ellipse path at one of two foci. An ellipse is a geometrically stretched circle, meaning that the planet to Sun distance is constantly changing as the planet goes around its orbit. Now moving on to Kepler's second law, or rather known as the law of equal area. A line joining a planet at the Sun sweeps equal areas of space during equal time intervals. So basically the planets do not move with constant speed along their orbit, rather their speed varies. The point of nearest approach of the planet to the Sun is called the perihelion, and the point of greatest separation is called the aphelion. Hence, by the Kepler's second law, a planet is moving fastest when it is at the perihelion and slowest at the aphelion. And at Kepler's third law, or rather known as the law of harmonies, the law states that the squares of the planet's orbital periods are proportional to the cubes of the semi-major axis of the planet's orbit, or rather can be simplified as p squared over m cubed. According to this law, the time of the planet's orbit around the Sun grows exponentially around its orbital radius. And now, hence, Kepler and his theories were critical in the understanding of our solar system dynamics, acting as a springboard to new theories that can be more accurately approximated in our planetary orbits. And now my answer to question 9. Does the planet move as the Sun orbits? Yes, the Earth actually oscillates slightly around its axis as the Moon orbits the Earth due to the Moon's gravitational force and pull. This is different to the Sun to Earth scenario where the Sun didn't move at all during its orbit. And now this is because of the Sun's huge physical size and mass, where the center of mass is actually within the Sun at its center point. And due to this, the effects of the Earth's gravitational pull is almost negligible to the Sun, and this is because of the Earth's smaller mass under Newton's law of universal gravitation. But since the mass of Earth is only 81 times the mass of the Moon, the center of the mass is not at the Earth's center point, but approximately 4,671 kilometers from the Earth's center, which is about 1,700 kilometers from the Earth's surface. And now to answer question 11 and 14. So with the grid lines turned on, the average distance between each marking is 0.49 astronomical units. And now time to compare our data on our 4 different experiments. So in our first experiment, we had an average planetary distance of 1.60 astronomical units, which corresponded to an orbital period of 752 days. And in our second experiment, we had a planetary distance of 1.181 astronomical units, which corresponded to an orbital period of 579 days. And in our third experiment, we had a distance of 1.08 astronomical units, which corresponded to a 323 days of orbital period. And in our last experiment, we had 0.957 astronomical units, which corresponded to an orbital period of 318 days. To ratio equation provided by Kepler's third law, p squared over m cubed, and then we can see that we do get, in fact, a constant of close to 1, which means that these results do follow Kepler's third law. And now to answer question 15, I fully expect Mercury to have the fastest orbital velocity and the shortest orbital period, and I expect Neptune to have the slowest orbital velocity and the longest orbital period. The reason for this is due to the Mercury being the closest planet to the Sun, which means it has a shorter orbital path and experiences a stronger gravitational pull. The Mercury's average velocity is being around 47.87 kilometers per second. For Neptune, this is because it is the furthest away from the Sun in the solar system. Neptune's average orbital velocity is only 5.43 kilometers per second. And given by Kepler's third law, we know that the planet's orbital period squared is proportional to the average distance cubed from the Sun. Therefore, for planets further away from the Sun, it will experience a greater orbital period, and vice versa for a planet that is closer to the Sun. And then finally, what have I learned from this experiment? I've learned about the 3 Kepler's laws about the planetary motion and how the planet's orbital distance affects its orbital velocity and its orbital period in regards to its Sun. And I've also learned Newton's law of universal gravitation with how a planet's mass does affect its gravitational force on other celestial objects.